think the eye works and why it's correct to use the circular arc, because our eye is globular and the back of the retina is a curved surface, so that what's happening at the back of my eye in my retina can be represented by an arc in front of my eye, which is why I've set up these geometric diagrams that way. And then there's basically, you know, the planar angle that you need, and there's basically only two theorems that you need to know to understand direct vision. And direct vision, the theory of direct vision, I think, is different from the theory of perspective. Perspective for me is representing 3D objects on a 2D planar surface by mathematical rules, whereas the theory of direct vision is applied to how your eye works. It's, you know, geometrical optics rather than paintings or drawings, yeah, or technical drawings. And there's only two theorems that you really need to know, and that is that objects have that proportion respectively as the angles under which they are seen. And I've got geometrical proofs in here, right? So I went through all the diagrams, did all the proofs, and also show in here, you know, certain things that people take for granted, but they shouldn't take for granted. So things, it's not as simple as saying, if something's twice as far away, then it's going to be half the size. You know, that's what ballers tell us, right?
Yeah.
But it's actually a lot more complicated than that, depending on the situation of your eye and how the object is, yeah? But when I measure visibles, then I'm always doing it with respect to the eye in a particular situation. The same way I asked you, Zach, what shape the table is. That depends on exactly the relationship between your eye and the table. And we can never forget that that's relative to exactly where you are and how you're looking at it. Also the inclination and the rake of your head and the way you look at things. And that stuff is a completely different way of measuring objects than tangible stuff is. Because one of the differences is, and this is why the geometry of vision is spherical, is that it's two-dimensional. You cannot possibly determine the distance of an object from your eye using geometry alone. You sometimes have depth cues. So for example, you could see that something is further away because you know it's a horse and you know the size of a horse, and you know you can relate to things, or grass that's further away will be lighter than grass that's closer to you. It'll be a darker green closer to you, so that you know that the grass, because it's the same color, if you were right up next to the far away grass, it would be the same color as the grass near to you. But you know that the grass is further away because the color is slightly, how should I say, diffused or lesser, a lesser intensity of green. But from a purely geometric point of view, you cannot tell whether something is very close to you and very small, or very far away from you and very big. It's called the so-called size, distance, invariance problem. And it's the thing that astronomers have to contend with all the time. They have no way geometrically of knowing whether the star is massive, as they tell us the sun is, and it's 92 million miles away, or whether it's only 3,000 miles away and 32 miles in diameter, or in radius, diameter, or whether it really is the size of a 5-pence coin held at arm's length. You cannot tell the difference in those things from a geometric perspective. And that's why you cannot see the distance of things, but what you can do is see the position of things. And that is the big distinction that we have to make, that yes, with our eyes, we can see the position of certain things in relation to other things, but we cannot ever geometrically, with our eyes, see the true distance of something. Again, I'm ignoring depth cues, as they call them, of which there are a few, but when we look at the night sky, these depth cues are no longer available to us. So that when we look at the night sky, for example, we can't tell geometrically whether that star's far away or not. That's when they have to play with things like light intensity and luminosity and spectrography, all spectrography to tell us all these fucking fairy stories, because they can't do it geometrically. One of them, the top one, is our 3D Euclidean world, and the bottom one here is a two-dimensional sphere, because the position of an object, if that's the only thing that you can find out, the position of the object, and you can't measure the distance from you, then everything appears to be the same distance. So everything appears to be on the inside surface of a sphere.
Yep.
At the same distance from the center point, your eye. Think of this as the geometrical space of visual perception with an eye at the center looking out. So what you see is basically visible figure on the inside surface of this sphere, the inside concave surface. You're in the middle, you're looking out, and your whole world of visibles, everything you see, every visible object that you see is actually basically being registered as a figure on the inside concave surface of a sphere. So I've talked about this before. The eye is very obviously globular. A few of these things are now in that document, so I'm kind of skipping forward a little bit. Yeah. So I hope that I've justified to you guys that when I'm looking at how the eye behaves in situations like railway lines or lampposts or things going into the distance, that it is valid for me because the retina is curved and because geometrically speaking, the center of the eye is the place where the rays cross over, they get inverted. So this is where the inversion happens. That's why the object looks to be upside down on your retina, or in fact it is upside down on your retina. There is a material impression. But these angles here, so this pink angle to the green angle, the proportion of that pink to that green is the same as the proportion of that green to that pink. Nothing is changed. Would you agree with that?
Yeah, absolutely.
Absolutely.
And that these arc segment lengths, because of what I said beforehand, this planar angle and the solid angle from the center of a sphere can be measured by the arc length of a great circle. If I was to continue this, it's a great circle of a sphere. Then we can basically, when we're looking at the phenomena of railway tracks, for example, then we are perfectly justified to use a circle of measure rather than a tangible straight. What a sphere looks like, but a visual aid does help. You can see that at the North Pole, these two lines converge, and at the so-called South Pole, they also converge, right?
Yep.
In spherical geometry, these two lines are supposed to be parallel to each other, and they converge, right? That's in the definition of the spherical geometry.
Yep.
Now, if I'm on a railway track and I look forward, then I will see the railway tracks converge to a point. And this is the important part. If I now turn 180 degrees and look the other way down the railway track, they're also going to converge to a point.
Yeah, they don't go spread out the other way.
They don't spread out, right? So basically what I'm saying is that that's also a very clear indication that it's spherical geometry we're working with, because only spherical geometry can do that. Converge in front of you and converge behind of you like the North Pole and the South Pole do. So your vision, that's another example of, you know, I'm not saying it's a proof, it's an observational experience that shows you that these axioms of visual geometry are spherical and that they are self-evident and that you can observe and experience them yourself.
Well, it's an evidence, I reckon it is a proof. It's an evidence that your vision is spherical.
For me, it is too.
Because you do know those lines are parallel.
Yes, I could walk down that railway track and I know they're not getting smaller. And the further I go, they're still going to converge. Yep. So it's, in that respect, it's just like spherical geometry is. Yeah.
Excellent explanation. just had a good aha moment there.
Yeah.
Good.
Oh,
Let me just skip through this document because I think this basically takes us through the document of the theorems that that are in that document. But I'm pretty sure I had some examples, yeah, to try and make this a little bit more, how should I say, easier for people to. So, explaining why lampposts, I've just put lampposts in there, and, I've tried to explain it a little bit more. It can be the same thing as a railway, what I just talked about, yeah?
Yep.
It's the same reason buildings disappear from the bottom up, same principle. Or the sunset, yeah? Or a brick wall, if you look at a brick wall, or a corridor.
Now, if I was thinking, if you had a long corridor like that and you put your head up against one wall all the way to one side and something down at the far end against the same wall, wouldn't that one side of it that's near the wall be cut off?
Like this picture here? A bit like this one? Like you will not see the pictures on the wall, these pictures that you have on the wall. You will lose sight of them quicker if you're closer to this side than you would of the pictures on the other side of the wall.
Yep.
Yeah.
That's what you mean, right?
Yeah, absolutely.
Yep.
You have them for everything. Yeah, great. Wow.
And I actually did a whole modeling of how a corridor looks so that, I can move the corridor wall backwards and forwards and show what's actually happening on the eye. And I hope you guys can see this a little bit, because this is where you can see that if you can now think of this as the eye, or you can think of it as your geometrical visual space, it doesn't really matter. Thinking of it as the eye is maybe easier for most people and not that abstract geometrical thing. But basically, as this wall moves further away from you, and when I say wall, I'm basically taking a snapshot of a corridor, let's say here, at where these two doors are, and I'm taking another snapshot further down the corridor, and another snapshot, another snapshot. This is what this plane represents here. And if I move that away, then what's happening on the eye, this red, what looks like a rectangle, is going to look more and more like a Euclidean rectangle. You will not be able to see that it's actually curved. You can see, because this is fairly close to you, that there is still a little curve on these lines, right?
Yeah, like the example you showed of putting something close to your eye and it looks spherical, and then.
That's right. So if I was to move this very close to my eye, then this rectangle will blow up and fill basically all of my eye here, and it will be very obviously spherical. But as soon as things get further away from you, then there is hardly any difference between you seeing it Euclidean and it being Euclidean. You will not be able to tell the difference, at least not from your eyesight. And that's, when I said, when I say spherical and people say, but Gavin, I don't see a curve, then that's what I was trying to explain. You don't see the curve because it's a very good approximation to the Euclidean world at normal distances of sight. And especially far away, you can't tell the difference. You can only tell the difference when it's really up close.
Yeah, really up close. I couldn't believe how much it curves.
If you go back a bit, Gav.
Yep.
You can see there's that diagram in the bottom right compared to the one in the bottom left.
Yeah.
Oh, that's right. Yeah, that is
more curve.
You can see it's curved, so that the plane's right up against to the eye, and you can see that what's being left on the eye, the material impression on the retina, is actually curved. Yeah, and it's only then that you could really see it. So I'm here only 1.5 away from the guy, and here I'm at 4.3. Yeah.
It's good to see this one. I've been lucky enough to see this one in animation.
I can do that right now. Hold on. I'll just open it up. So you can see I basically modeled a corridor here with roofs and stuff like that, I modeled a sphere for the eye. I modeled the horizon, the azimuthal, or what do we call them? The longitude circles and latitude circles. I made various lines and walls and planes and spheres. So, but basically, if I zoom out a little bit, hopefully you guys can see the overall picture.
Yeah.
So I can now move this closer to the eye, and if I now zoom in a little bit more, then you guys can see that the thing is curved. If I turn it around a bit, yeah, then that's the picture I was basically showing, yeah. And if I zoom out a little bit more again, oops, and move the wall or the placing plane away down the corridor, and now zoom into this part, then you can see that it's, you know, indistinguishable from a rectangle now.
Yeah.
Yeah. There's actually a couple of experiments you can do that will show you that your vision is spherical. And again, I think we've got a couple of videos on that, Glenn, which we should really maybe just show. But if you have objects up very close to you, then you can actually see the spherical nature of your vision. But if things are kind of like 12 inches away, then the world starts to look very Euclidean again. When it's up close, you can see things appearing to be spherical in certain circumstances. So I think what I want to say there is that if people don't believe that vision is spherical, or that visual perception is spherical geometry, then there are experiments that you can do to prove it to yourself, which I think is highly important. Because me saying that we have a spherical geometry of vision, but you see things Euclidean, is a kind of, for a lot of people, maybe a kind of cop-out, right?
Yep.
So if I was, for example, to draw a spherical triangle in here, then and bring this up very close to your eye, so these are three walls that are perpendicular to each other, yeah. But if I bring these things closer to my eye, then the thing will actually start to look spherical. These lines will start to look curved, yeah.
Wow.